All right, this lesson is Pre-Calculus 30, Section 3.3 in your McGraw-Hill Ryerson Pre-Calculus 12 textbook. Starts on page 126 if you're following that textbook. What we're going to talk about in this lesson is the factor theorem. No matter what textbook you're in or what class you're in, the factor theorem is going to be explained here. So what we are looking at are these four important questions. That's what this lesson is all about. The first question is this: how are factors and remainders related in regular arithmetic problems? So we're going to explore that. Second question is, what does the factor theorem actually state? That's kind of the main point in this lesson. How do we find possible factors for polynomials, and how do we fully factor a polynomial like from scratch with no help? Okay, that's what we're going to do today. So let's explore the first question here. How are factors and remainders related? I did this example for you the other day. If we were to take 12 and divide it by 4, what we do is we say, okay, how many times does 4 go into 12? Well, it goes 3 times, and it goes 3 times exactly, which means that there is a remainder of 0. Now, 4 and 3 are factors of 12. If I were to take the same number 12 and divide it by 5, what you do here is you'd say, oh, it goes in twice, that's 10, but now we have a remainder of 2. So the question I'm asking you, are 5 and 2 also factors of 12? And you're all shaking your head, of course, you'd say no. So how are the factors and remainders related? Well, if we were to do this one more time, and I'll just do it quickly one more time, let's say 12 divided by 6. Well, 6 goes into 12 2 times, and it actually goes in exactly 2 times. So we know that 6 and 2 are factors of 12. What you should be noticing is that when you do division, a dividend divided by a divisor, that divisor is a factor when the remainder after that division is 0. Okay, so how are factors and remainders related? Well, we're going to say that the remainder is 0 when dividing by a factor. Okay, if it isn't truly a factor, the remainder is going to be 0. And of course, what follows this is the quotient. That's the number up top here, is also a factor. So we're going to get 2 factors right away when we divide and we get 0. Okay? So if we apply this to what we've been learning with the remainder theorem, okay, then, and I'm just going to actually just skip back here, so I hope you have that written down. I will come back to this slide, but let's just go back to some of the things that we've done here before. Okay, there's your last assignment. Here's some last questions. Okay, so this is a bit messy, but let's just go back to this example. So you see what we did here, right? I had this polynomial, x squared plus 10x minus 24, and I divided it by this binomial. I got a remainder of 0, which means that this is a factor. Yay. It also means that the polynomial that these coefficients represent, which is this right here, is also a factor. You see that? So we took this polynomial right here, and when I divided it by a certain binomial and got a remainder of 0, I all of a sudden knew that this was a factor and whatever the quotient was also a factor. Okay? So that's what we did last lesson. Now, we didn't talk about factors last lesson, but now we're talking about factors. So we've answered question number 1. Let's talk about what question number 2 asks. What is the factor theorem? So if we were to take a good close look at that, let's go to the textbook. And I'm just going to back up a little bit here for you. So the factor theorem is right here. Now I'll clip this into our notes so we can expand that a little bit if we need to. And doodle on it or whatever we need to do. Let's just throw that down here. Really small. Okay, so here's the factor theorem. Sorry about this mess here. But it says that x minus a, so this binomial in this form, x minus a, is a factor of a polynomial in x, and that in x means it's just in terms of x, right? That's the polynomial p of x, if and only if p of a equals 0. So if the remainder is 0 when you divide, then this x minus a is a factor. And of course, because you know about the remainder theorem, you don't actually have to divide fully to find out if some binomial is a factor. Okay, I know that's a lot of words there. I'll say that again. If you know that this value p of a is 0, then you can automatically say that x minus a is a factor. That's what the factor theorem states. All right. So, oh, sorry, I'll just go back there. Have that up there. So, just let's see. I'll pick an example here. Okay. So x cubed minus x squared minus 5x plus 2. Okay, this is a function here, or a polynomial of x. Let's use p, like the book does all the time here in this section. So that's a polynomial, and I want to know, is x minus 1 a factor? Okay, so is x minus 1 a factor? All right. Because of what we just learned, if you could find out quickly what the remainder is when you divide these two, then you can tell whether it's a factor or not. So you have several options, don't you? You could do long division, and don't want to do that one probably. You could do synthetic division, and it's better than long division. You probably don't want to do that. What you could do is say, hey, I know what a is. A is positive 1. I'm going to find out what p of a is. And that's going to be probably your quickest, right? You could probably do this in your head as well. Just put 1 in there. That's going to be 1 minus 5 plus 2. So what do we get? Well, that's 0, negative 3. That would be the remainder if we divided this polynomial by this binomial. Everyone see that? That's the remainder theorem from last class. The factor theorem now says that because this remainder is not 0, x minus 1 is not a factor. I'll say that again. Because the remainder is not 0, that means that this is not a factor. Because if we go back to our first example, it would be like this right here. We have a remainder. See, that's not 0. So that means that this one is not a factor. This one is not a factor. All right, so let's try another one. Let's just try, instead of x minus 1, let's try x plus 2. Let's see if this one is a factor, okay? Let's see if that is. Well, if we go p of, should I do positive 2 or negative 2 here? What should I test? Thank you, negative 2, very good. So that's going to be negative 2, and I'll just write this out for you. Okay, it's 5 times negative 2 plus 2. So if we evaluate this now, that's going to be negative 2 cubed is what? Negative 8, very good. Negative 2 squared is positive 4, so we're subtracting positive 4. This is negative and a negative, that's going to be positive 10 plus 2. So what do we get? We get, this is negative 12, this is positive 12. So we add those up, we get a remainder of 0. Ta-da! 0. Hey? Our friend, 0. What does that tell us? Verbalize that for me. What does this mean? It means that, what? Finish the sentence. Yeah, keep going. Okay. X plus 2 is a factor of Did I quote you correctly? That equation that you wrote down. Yes. X plus 2 is a factor of this polynomial right here, x cubed minus x squared minus 5x plus 2. That's what that means. That's the factor theorem right there. Any questions? Good. We're not done. Gotta keep. Yeah, I know. I'm sorry. We gotta keep going. There's a few other things you need to know, but that is the basis of this whole lesson. That is the if you understand that, that's great. My question to you though is, we have some more questions right here. Number 3, how do we find possible factors? We have to look at this. Because if we go back to this question, notice that I gave you this factor and we tested it. I also picked this factor for you and we tested it. Now, why did I think that these two binomials could be possible factors? And that's what we want to explore right now. Okay? Now, there is a special, what is it called? Theorem. Nope. Yeah, is it a theorem? It is a theorem. There's a special theorem that's actually kind of confusing, but it's really easy. It just, you know how they get wordy sometimes in textbooks. So this is the theorem right here that is going to help us. It's not the factor theorem. It's the, oh, are you ready for it? The integral zero theorem. Yes, integral zero theorem. You're my hero. Exactly. Excuse me. So what does the integral zero theorem state? It states this. In the technical terms, it says this. If x equals a is an integral zero, so an integer that is a zero of the polynomial, p of x, with integral coefficients, then, that's integers, then a is a factor of the constant term of the polynomial. Oh, I know. That's a lot of words. It looks very, very confusing. If you recite this to some stranger on the street, they will either be very impressed or they will refer to you to psychiatric care. It's one or the other, okay? If you were to recite this to me in the hall from memory, I would be thinking you're sick, okay? But, you know, normal people would be impressed. No, I'm just kidding. So, let me tell you what this means, okay, because it's really easy. I'm sorry if you were writing that down. It's in your textbook. This is what this means. I chose these possible factors, right here, x minus 1 and x plus 2, because, and this is what the theorem states, that any binomial that is going to be a factor of another polynomial, like this value, this a term right here, in this case it's negative 2, or this value of a, in this case it's positive 1, should be, or has to be, a factor of the constant term here. Yes, has to be. Oh, minds are blown, right? Now, isn't that easier than this explanation over here? Hey, yes. Yes, it is. Okay, just agree with me. This goes faster if you just agree with me, okay? That was a joke, but yes, thank you for agreeing with me. Oh, good question. Does it matter if it's positive or negative? Well, here's the thing, okay? Let's take this exact example here, right here, and I am going to cheat just a little bit, and I'm going to lasso this puppy, and I'm going to copy it. Hopefully it'll all copy. And I'm going to put it right there. I'm going to post it for you. I'm going to clean it up just a little bit here. Okay? So if this is the polynomial, the possible factors, okay, are going to be, and you can list them. The possible factors are going to be x plus 2, because that's a factor of plus 2. Also x plus 1, x minus 2, and x minus 1. So what you would do is you'd list all the factors of the constant, and you would basically plunk it at the end of a binomial. And these are your possible factors. They won't all be factors, but they are the possible ones. So these are the ones that you would choose to test. See that? If I had another polynomial, let's see, x cubed minus 15. And let's say that's just all you have. That's your polynomial right there. Okay, p of x. So you would test factors like what? Throw them out. Sorry? X plus 1. Is that a factor of negative 15? Yeah, sure is. Right? X what? What are some other ones? Minus 1. Yes, x plus 5, I heard. X minus 5. X plus 3 and x minus 3. Anything else? Yeah, x plus 15 and x minus 15. That's right. Now, these are all the possible binomial factors of that. So you would test these ones. A little hint, usually the ones with the smaller a values, you want to test those maybe first. Not always, but those are the ones you kind of want to test first. Because the chances that x minus 15 is going to be a factor, you know, the largest number, is the probability is low. Okay? But we could factor this. X cubed minus 15. We could factor this pretty easy because I need to find one factor first. So let's turn it over to this question here, and let's do it. You don't have enough room. Too bad, so sad. You write it. Okay. I'm going to lasso this thing again. I know that's a word you guys like apparently over there. Sure, am I saying that wrong? Lasso? Lasso? Lasso. I knew a guy named Lasso once. Okay, so here's the polynomial. And we're going to test these factors. So should I do long division to test each one of these factors? No. Should I use synthetic division? No. What should I use? The remainder theorem. Thank you. Why don't we do that? Okay. So let's do P of what? Let's test this one right here. Let's try -1. Awesome. You do not have to write this all out like I'm doing, but I'm just showing you what I'm doing. So P of -1 is, let's see, that is, okay. That's going to be -1 minus 15. Is that going to give us 0? That's not equal to 0. Okay. What else here? Okay. Okay. I'm just noticing something. This is actually going to be prime. I think that yeah, this was not a good example to do. But if you notice this, like I just noticed this, and I should have noticed it before, but you guys distracted me. You guys always distract me. We picked this at random. Do you guys see that we're going to run into a problem here? Okay, why? Why are we going to run into a problem? Is there anything cubed that is going to give us 15 in this list? Any integer number that when cubed is going to be 15? No. So guess what? None of these factors, none of these binomials are going to be factors. Okay? But you may not realize that until you've tested a few. You say, I'm not getting any factors here. Well, how does that work? So, let's pick another example that's actually factorable. And maybe I won't pick one at random. Let's do this one. Okay? Y equals, or f of x equals, p of x equals 2x cubed minus 5x squared minus 4x plus 3. And we are now answering the question right here, how do we fully factor a polynomial? That's what we're doing now. Okay? We're going to fully factor this thing, and that's all we're given is just the polynomial like that. Okay? So, the first step is to choose possible factors. What are possible binomial factors? We look at the 3 there, right? So x plus 1, x minus 1, x plus 3, x minus 3. Those are all of the factors of 3. Yes? We good? All right, so let's test them real quick. Let's test, well, this one's easy because you just put plus 1 in here, right? So 2 times 1 cubed minus 5 times 1 squared minus 4 times 1 plus 3. That gives us 2 minus 5 minus 4 plus 3. What does that give us? 0? Nope, doesn't. This is -9, and that's plus 6, so that's not equal to 0. So let's test another one. What about 3? And yes, you might have to test a few before you run into your first factor. That's called life. It's what happens sometimes. So what's this? 2, we're going to do -3. You know, groaning all over the room. You know what? Suck it up. All right. So what's this? 2 times, what's that? 9. Oh, dagger through the heart. Did you really say 9? Ow, that hurts. Okay, -27. I will. Okay, it's okay. It's all right. My heart stopped for just 1 second there. What's this? Don't say 6. Thank you. Okay, so this is +9. So that's minus 5 times +9. Got that? All right, and plus 12 plus 3. So is this going to work or no? Well, that's negative what? 54. That's going to be negative 45. That's going to be plus. Okay, so that's plus 15 over here. Does that work? No. Okay, not equal to 0. All right, so keep going. Does anyone see a factor? -1. So this one, x plus 1, you think? Okay. I guess we could have started with this one. You might want to start with the first one on your list. You don't have to, but I wanted to just go through a little pain with you here, just to show you what it's going to be like. So let's try this. 2 times, let's do a negative 1 here, 5, negative 1, 4, negative 1, plus 3. That's going to be, cubed. That's going to be negative 2. That's going to be minus 5. That's going to be plus 4. That's going to be plus 3. Negative 7 plus 7. That equals 0. Ta-da! Very good. So what does this tell me? Factor theorem says that what? X plus 1 right there is a factor of this polynomial. Wonderful. That is step 1, okay, in fully factoring this. Now that you have a binomial that you know is a factor, now what we do is we go ahead and now actually we divide the polynomial by that factor. So now you can just use your synthetic division. Let's put the negative 1 there. Okay, so we've got cubed, squared, to the 1, and to the 0. So we've got all of the terms accounted for. We go 2, negative 5, negative 4, positive 3. We're going to have a remainder underneath there. That's not going to be part of our quotient polynomial. So, you guys should be pros at this right now. Okay, is everyone doing this question with me, or am I just the only one doing it? Because guess what? I know how to do this. You guys should be doing this. Okay? All right, I'll do this. Okay. So you guys go ahead and finish that, and we'll see if you get the right quotient. All right, did you get that? For quotient? Okay, and remainder is 0, so that confirms that we did something right here. Now, when we're factoring this, what you want to do is don't forget about this x plus 1. So we are factoring. So now we've done the first step of factoring by identifying 2 factors. That's 2 factors. Now, if we are asked to fully factor this original polynomial y here, then we have to check to see if this can be factored further. Okay? Now you may get, when you get to a quadratic here, you may be able to just factor by sight, like we did in grade 10, factor by sight, or use your, decomposition method, or you could use the factor remainder theorem, synthetic division, whatever you need to do. But you need to see if this can be factored further. So can this be factored further? And so what we do is we look and we say, hey, are there 2 binomials that will multiply to this one? So if you were using your intuition, you would say 2x squared here, that's going to be 2x times x. I have to have numbers that multiply to positive 3. So if I just chose 1 and 3, I realize that this is a negative, so maybe let's make these both negative. And does that get you this trinomial here? Do a little FOIL. 2x squared minus 6x minus 1x gives you minus 7x. And then negative 1 times negative 3 is positive 3. All right, so you could factor this by sight. Now, if I went too quickly for you there, or if you have no idea what I just did, you need to go back to Math 10 and either watch some more videos, okay, on decomposition or factoring quadratics, or you need to come talk to me. We'll get you figured out here, okay? But that appears, if I've done this correctly, double check, yeah, looks good. So this is now the fully factored form of the polynomial. That is fully factored. Okay. There's one factor there. Here's another factor here, and a third factor. Okay? So this is what you're going to have to do. This is a question you're going to have to do. That's the whole point of this lesson. All right. Question. Yep. So that's a good question. On this list, could more than one of these be factors? Yes. Once you find one, instead of checking all the other ones the same way, you might want to just go right to your division, so you can get to another polynomial here. Do you know what I mean? Like that's gonna be the quickest way. So this method would be your best method. But if you wanted to go through, yeah, you could go through and check. You got this one as a factor. You could check this one. You could check this one. Check this one. But as you see, this one is a factor down here. That's what we ended up with. So, but you might spend a lot of time checking factors that aren't, or binomials that aren't factors. So yes, more than one on that list totally could be factors of a polynomial. All right, so that's the lesson on factor theorem and factoring polynomials. Good job, everyone. So key ideas, page 133. This is a good summary of what we've done here